do something in here because I drew a really big top hat.
Hi, everybody. It's time for us to get started. And I think I'm a little bit, just a little bit late. But the very first thing I want to do for this class is, first of all, announce and make sure that I'm in the right position myself. So this is the mathematical analysis class, and I'm John Whitaker. I'm going to pass out the syllabus. We're going to spend a few minutes going over the syllabus, even though there are certain things, everything that I'm going to go over is written down in the syllabus. But we'll make sure that there aren't any mistakes in the syllabus, and I'll emphasize a few things by writing them on the board. I'll call roll after that, and then we'll do a little bit of preparatory work for the class, proving techniques. Is what I'll talk about. Okay, as I said, even though this information is listed on the syllabus, I'm going to write it on the board for emphasis. As you can see, we're video recording the class. These videos will be put onto YouTube that will eventually be linked to Blackboard that you can access through MySSU. And probably next time I'll start off the class by showing you how you can access it. So this first class lecture will just do as is and kind of use it as a model. But first of all, I want to let everybody know, I think everybody in here, except maybe one person who hasn't had me before, but I think everybody else has had me. But my name is John Whitaker. And on the syllabus, it lists my office, and so I'll write it on the board as well. So that's administration, 115. Most of you know the administration building is the building that's part of Massey Hall, or connected to Massey Hall. And so I hope that most of you know where my office is, but it is in the administration building, 115. The time that I'm going to be there, the office hours, they're going to be Monday and Wednesday from 10 until 11, and then again from, I think, 2 to 3. On Tuesdays and Thursdays, for almost every week, it's going to be from 1 to 3. And then on Fridays, I'll have office hours from 10 until 11. Those are times that I'm pretty much guaranteeing that I will be in my office. On occasion, things can occur. Meetings can come up that I didn't know about, and that they will say to me, please come to this meeting, and I will have maybe this meeting during my office hours, at which time I'll put a note on my door saying the office hours have been canceled or moved. But they will happen. Those times will happen seldomly. Okay, very seldomly. So these are times that I'm pretty much guaranteeing that I'll be in my office. I say that, but this first week, there's one of my colleagues who is out of town, and during this week, and so I will be substituting for Dr. Lee on Tuesdays and Thursdays, and I probably will not have the office hours for this week on Tuesdays and Thursdays because of being a substitute for Dr. Lee. The other thing that I wanted to go over, the next thing I want to go over in the syllabus is I want to talk a little bit about the book. Dr. Dakota, you see that sometimes it gets a little fuzzy and then I come into focus. The next thing I want to talk about, is a little bit more of contact information. So as you see listed there, my phone number, 740-351-3630, and email is another good way of contacting me. It's jwhitaker@shawnee.edu. So overall, what I'm trying to emphasize here is who I am, where I'll be, when I'll be there, and other ways of contacting me. Phone is a good way to communicate with me. If I'm not in my office, please leave a message. If I'm there, almost surely I will pick up. There are occasions when I have someone else in my office, and I just let the phone ring. That does happen every once in a while. So I'm in my office, sometimes I don't pick up because I'm meeting with somebody. But please leave a message. I'll get back to you. Email is also a good way to contact me. It's a little bit, I think, a little bit difficult to communicate sometimes mathematically. via email. There's not the symbols there. It's kind of hard to describe certain things just with regular words. But it can be done. And in addition, our copier now has the capability of scanning things, and we can import them to our email. So I can write down on a sheet of paper certain things and email them to you. Okay, you have questions. So it's still a good way to communicate email. I check email 3 or 4 times a day during regular business days. On the weekends, I check email. Saturday and Sunday, maybe once each of those days. And I usually get back to people within 24 hours. Every once in a while, an email will not go through, or will go to our junk email. Even if it comes from another Shawnee account, that can happen. So if you don't hear from me in a couple of days, and you need to hear a response from me, send the email again. Well, the text is this book by Arb and Scherber. It's Introduction to Real Analysis. This is the book. I'd like for you to have the book. We're going to go over chapters 1, 2, 3, and 4 of this text. Most of the proofs that I will do and statements that I will do are in the book. On occasion, I will present a proof that's different than the proof in the book, but most often I'll be following what the authors do. Sometimes I'll put in a little bit more details than what they do, a little bit more explanation. But most times it'll be just what they did. There are homework problems that sometimes I will assign from the book to be turned in. This course is a little different than some maybe other courses that you've had, like in the calculus series. What I envision for pre-calculus when I teach it is I'll cover material, a section of our book, and then we'll assign 20 or 30 problems for you to practice the technique that we're talking about, differentiation, integration, that type of thing. That doesn't happen in this class. Rather, what happens in this class is we're learning about the material that's the theory behind why techniques work. Okay? We're learning why certain facts are true, the proofs of them. And so you won't be getting homework after every class meeting. Your homework will kind of be to go over the material and that we've covered in class, to be able to say, I can produce those logical arguments. I understand why these facts are true. I know what the definitions are. That's going to be homework that you can do. So reviewing the notes and knowing the information are going to be things you can do in preparation for exams. Okay? There's a catalog description on the syllabus. I'll let you read that. There is, so that, I said chapters 1, 2, 3, and 4, but really we'll get into chapter 5 just a little bit, I think. The continuity. Let me look. Yes, it does go into chapter 5 just a little bit. Okay. The grading is the next thing that I want to emphasize. So what we'll have in this class is there will be 5 to 6 homework assignments. Things I will say, here are problems I want you to turn in. You can work together. It's okay. You can come by and ask me questions. But I want your work that you submit to be your own work. If you got some ideas from somebody else, that's okay. But you follow them your own. You write it up yourself. You make sure you understand for the homework. And that'll total about 120 points. There will be 2 in-class exams. Those exams will consist of, generally, being able to restate proofs, statements that we've had. There will be some problems that you'll have to apply the theory to, but a lot of the work on the test, at least 60% or more, 60% or more, will be things that we did in class. And I'm just asking you to reproduce them, that you understand them. And so some people think, well, I can memorize it. And I think that is true. You can't memorize the material. But what we're looking for is for you to say, I know why this is true. It's based on these previous facts, and I can string together a logical argument for why this next fact is true. That's what we're looking for. There will be a final exam. It'll be comprehensive. It'll cover the major ideas of the course, the major concepts of the course. And I don't list any dates of when things will be done in terms of grading material, except for when the final exam is. So on the syllabus above the table that I have for letter grades, you'll see that the final exam will be on Wednesday, May 6th, 2015, from 12 to 2 o'clock, essentially, in this room. Shawnee State is a plus-minus grading school, as I think all of you know, and so I have a grading scale listed below there that tells you what your course percentage will equate to in terms of a letter grade. In particular, if you make 92% or above, that's going to be an A. If you make 90 or 91%, I'm going to write down A minus. If you make 88 or 89%, that's going to be B plus. 82 through 87 is going to be B. 80 and 81 is B minus, and you see the rest of it listed there. There's a disability statement. Please take a look at that. The attendance policy is that you're expected to come to class. If you happen to miss a day, well, okay, I'm not going to take away points. You're not going to get points for coming to class. Okay, either way. The reason to come to class is to learn the information. Here, we're going to record the lectures. Okay? And so you say, well, I'm going to see the recording. Well, okay, I understand that. But there also is going to be the missed opportunity of asking questions. Okay? So I wouldn't miss class unless there's a big reason. If you happen to miss a class date when something is due, homework assignment is due, or when we're having a test, you can make up that work as long as you have a valid excuse. Validity of the excuse is going to be determined by university policy. If you're on the sports team and you have a sports meet, that's a university excused absence. Okay, that's allowed. If you're very sick and you can contact me right before the exam or sometime a little bit before the exam, say, look, I'm just sick. I'm going to say, okay, it makes sense to me. We all get sick, and you'll be allowed to make it. But you can't just say, I wasn't ready, or there has to be a legitimate excuse. Okay? We will cover, in the course outline, chapters 1 through 5, not all 5, part of 5. And so the important things that we're going to be doing is an introduction to proving techniques. That's going to be today and part of our next meeting on Wednesday. Then we'll look at properties of real numbers. Main thing we'll look at for real numbers, a lot of it, main things will have to do with absolute value. I think that's going to be an important part of this course, working with absolute value function. There will be properties of real numbers, sequences. There'll be sequences. Will be chapters 2, I think, 2 or 3. And then we're going to talk about a lot about sequences: convergent sequences, Cauchy sequences, monotonic sequences, bounded sequences. There's lots of things. And in calculus, we don't emphasize that so much, but in this class, it's going to be something important to us. Then the next chapter has to do with limits of functions. That's something that's in Cal 1. You learn about taking limits of functions, okay? And then continuity of functions. That's also something that's important. It's maybe just a section in Cal 1 or a section or 2 in Cal 1, but there's a lot of important theorems that have to do with a function being continuous and what you can say about it from that. And so we're going to look at some of those theorems. So it involves, what we'll cover involves chapters 1 through 5 of our text. This all fit on one page. Somebody might ask, well, you don't say anything about a calculator. We're not often going to be dealing with numbers. So we're a math class. There will be some numbers, but it isn't all the time. There'll be more conceptual ideas here and logical arguments. This course is about stating why certain things are true. What things are true, what things aren't true, what are counterexamples. Maybe some statements somebody might wonder about whether it's true or not, and what is true and how come it's true. And we'll have a lot of basic definitions from which we work. It's one of the beautiful things about it. All right, having said that, let me ask if anybody has any questions of me. I have a question of you. Is the clock correct?
Yes.
Wonderful. Corey, may I borrow your pencil? I very seldom will call roll, but today I'm going to call roll. So if you would please indicate that you're here when I get to your name, And if I mispronounce your name, if you'll let me know, it'd be nice. If you want to be known by something else, Captain America, you let me know. Mariah, I see you're here. Jonathan, I see you're here. Dalvin is not here. Samantha's not here. Corey is here. Bradley's here. Brad's here. Melissa Martin. Hi, Melissa.
Hi.
Chuck is here. Mary's here. Adam's here. Audra's here. Megan is here. Mark is not here. Thank you very much. Okay, I'm ready. The introductory thing I want to do is about proving techniques. Okay, so that's what we're going to talk about. Proving techniques. So, give me 1 second. I'm going to talk about 6 or 7 proving techniques, and what we think of in terms of these proving techniques. These are common arguments used in analysis. The most common of which is a direct proof. So I'm going to list 6 or 7 things here. So, direct proof. So what do we mean by direct proof? So, in general, if P then Q statement can be proven by real fuzzy. Okay. If P then Q can be proven by assuming P occurs, then using definitions, previously proven facts, innovative constructions, and algebra. Logically progress towards concluding that Q occurs. So these if P then Q statements are of this nature. If P happens, then that's going to force Q to happen. Okay? If Alabama were in the national championship game, they'd win. Okay? But they're not. So in the proving technique, I'm not trying to be that comical. They're not. In the proving technique of if P then Q, you've got to assume the if part, the thing that you're talking about, is occurring. Does that make sense to everybody? You put yourself in the situation that you're talking about. If P happens, well, let P happen. Okay? And then we say, we want to show that Q had to happen. Okay. So I'd like to do an example of this. So the examples that I'll do will be not heavy in terms of involved statements or proofs, okay, as examples. So they'll be mine. Let me get something. Okay, so as an example, if x is greater than 0, then x squared is greater than 0. So Megan, here's something I want to show. What am I talking about? I'm talking about if you give me a real number that's positive, when you multiply it by itself, you know what you get? A positive number. That's what I'm trying to show. Okay, so here's where I'll start this. First of all, I indicate that I'm doing a proof. And so what I do is you either write down the word proof or just PF for abbreviation for proof. And we're doing a direct proof, so we assume the first part. We say let x be a positive real number. Be a real number greater than 0. All right, this way, x being greater than 0. All right, so one thing that I'm going to assume that we've been shown, even though it's not true at this point, but it's a previous fact, I'm thinking that if you multiply both sides of an inequality by a positive quantity, you retain the same direction on the inequality. So that's what I'm going to use as a fact. So as long as I multiply both sides of these inequalities by a positive quantity, the result still retains this inequality. What I'm going to multiply both sides by is x, because I want to get x squared involved. Is that okay? So this means x times x is going to be greater than x times 0. Because I'm multiplying both sides of this inequality by a positive. Well, what is x times x? What's the symbol for x times x? So x squared is greater than, and what's anything times 0? 0. And that's the conclusion I was trying to get. Is that okay with everybody? That's the conclusion. So that ends my proof. I've done the logical argument, and it's all based on assuming what we have, using the fact that if I multiply both sides of an inequality by a positive quantity, I retain the same inequality, and then just simplifying this. That's all it's involved. I put this little box here and I kind of colored in. That's the indication that we're done with the logical argument. We're done with the proof. That's it. Well, that's an example of a proof. Is that okay with everybody? Okay, so that's a direct proof. Took the if part, we assumed it was true, used the previous fact, did a little computation, we got the result, the conclusion, followed logically from the hypothesis, the assumption. That's a direct proof. Let's look at another type of proving technique. It's called the contrapositive. Proof by contrapositive. So, if P then Q can be proven by proving its logical equivalent if not Q, then not P. That's called the contrapositive. Directly. And so as an example, let us prove this statement. If 7 times m is an odd number, then m is an odd number. That's what I'm. In the statement offered, there's some assumptions being made. When we talk about 7m, even though I didn't say it explicitly, Mary, even though I didn't say it explicitly, it's understood, okay, it's understood, Melissa, that m is some kind of integer, okay, plus or minus counting number. So here, I'm going to start the proof, and I'm going to let the reader, and that, in this case, you guys, know how I'm going to proceed in proving it. So Chuck, I'm going to say, by contrapositive. So Chuck, what that means is I'm going to prove that if m is not an odd number, then 7m is not an odd number. Is that okay? That's what I'm going to prove. But really, I'm going to do that directly. So here I'm going to say, suppose m is not an odd number. When we're talking about integers, you don't fall into one of two categories only. You're either odd or you are even. So that's what we mean that m is even. And you see that I'm using words in the proofs. It isn't numbers, there's letters, the symbolic representation of what we're talking about. But we're using words. So we're using these kind of words to connect previous statements like so, thus, therefore, consequently. Okay? To connect what we said before. And there are periods involved. I'm kind of writing paragraphs here. But I'm not such a stickler for these types of things. But that's the way we proceed. So m is even. Well, what does it mean to be an even number? What characteristic is out there? We didn't do the definition. That's the right definition. M is a multiple of 2. So m is equal to 2 times k for some integer k. Thus, 7 times m is equal to 7 times 2k, which equals to 14k, which equals to 2 times 7k. So, I'll give you a second. 7m, well, wait, I should say since. K is an integer. 7k is an integer. Okay, so remember our goal here was to show that 7m is not, what's our goal? We remember what we're looking to try to do? It's not odd. That's what our goal is. And what I'm just going to summarize here is that, so 7m, what was 7m? It was 2 times 7k. 7k is an integer, so it's 2 times an integer. So 7m is 2 times an integer. That means 7m is an even number. Thus, 7m is not odd. And that concludes the proof. And it's proved by contrapositive. I prove the equivalent statement to the original statement. Is that okay? The next proving technique I'm going to talk about is called proof by contradiction. And here's what it says. It says the statement if P then Q can be proven by contradiction. By assuming P occurs and assuming that's a good place to stop. Oh yeah, have a good time. And assuming Q or not Q occurs. So Q doesn't occur. So you're getting to assume two things. P happened, but Q didn't. Okay? Then logically proceed until an impossible conclusion is obtained. What I mean by this is the following. You assume that P happened. Put yourself in a position of what you're talking about has occurred. And you say, well, what if the conclusion didn't happen? And you start working. Well, that means this will happen. That means this must happen. And then that means this must have happened, which you know there's no way it could possibly happen. So this last thing. And you say, well, did I make a mistake in my reason? No. So it must be that there's a mistake in an assumption that I made. In the if-then statements, if P then Q, we must assume that the P happened so that the statement applies to our situation. So the thing that we must have assumed that is incorrect is that the Q didn't happen. That must mean that the Q did happen. Thus Q occurred. Must have. Okay, let me give an example. Listen, at any point you can't read something on the board, just let me know. No problem. Okay? If x is greater than 0, then 1 over x is going to be greater than 0. Okay, so I want to prove this. And I'm going to do it by contradiction. So what is it I'm trying to prove? I'm trying to prove if you give me a real number that's bigger than 0, then it's reciprocal, it's multiplicative, inverse. It's greater than 0. And I'm going to prove it by contradiction. So I'm going to again tell the reader what I'm doing so that they know how I'm trying to proceed. Okay, so what am I going to assume? I'm going to say, suppose, I'm going to assume the P part. What's the P part in this book? And assume, okay, let me stop for a second. Chuck, for our statement to apply, we got to assume the P part. So assume x is greater than 0. What I'm going to do that's extra that I don't have to do is say, well, what if the opposite of what I wanted to show is true? And assume 1 over x. What's the opposite of 1 over x being greater than 0?
Less than or equal.
Okay. And now I'm going to start working. Okay? And maybe I get some statement I say, that's impossible based on these two assumptions. Where this assumption is fixed, this assumption might not be true. So we say, if it is true, what happens? Oh, we get something stupid. So I must have assumed something wrong. Incorrect statement. All right, look, here's one thing. I got an inequality, and I know x is greater than 0. I'm looking at this inequality. What I'm going to do is multiply both sides of this inequality by a positive number. What do I know that's positive? The only thing I've talked about that's positive in this problem, in these short lines, the only thing I've talked about this problem is that's positive is what? What's positive? X. So I'm going to multiply both sides of this inequality by x. And it keeps the same inequality. So x times 1 over x must be less than or equal to 0 times 1 over x. 0 times x. I'm multiplying both sides by x. Well, what's x times 1 over x? 1. So 1 must be less than or equal to. That's my conclusion. 1 is less than or equal to 0. I know that is impossible. That's not true. Okay? That's a contradiction. The way that we symbolize contradiction are two arrows running into each other from opposite directions. Okay? Mary, I'm not good. Corey, I'm not good at writing that. So this is kind of the sneaky way to write it. You draw a line, and then you draw an X on the line. And that's two arrows running into each other. That's what you do. That's what I mean, you see, it's two arrows, right? I'm not good at doing that. That's the way I do. Okay? That's the way we symbolize that. And what does that mean? It means something, since we got a conclusion correctly, based on what we were assuming, but our conclusion is something that's impossible, it must be the case that something we assumed was incorrect. Something we assumed was wrong. The only thing we had any wiggle room to assume was this guy. This guy is wrong. So the opposite of it must be correct. That means that 1 over x must be greater than 0. That's proof by contradiction. Okay, so that's 3 proving techniques. Okay. The next proving techniques has to do with a specific type of statement. And really it's a proof by cases. So I'm doing something that I kind of consider proof by cases. Okay? It's a common proving technique and works for this type of statement. So I think this is my 4th proving technique. Is that right?
No.
Okay. So here's what I want to do. If P or Q, then R can be proven by showing 2 things are true. The first is that if P, then R, my R looks pretty bad, and you have to show if Q, then R. I want to say this is a proven technique which is considered a proof by cases. Look, the statement is if P happens or if Q happens, then R must have happened. So that means if one of those happens, R had to happen. So you have to show P happened, then R happened, and you have to show if Q happened, R had to happen. All right, so let's look at an example. And the example I'll show here, it doesn't initially seem to fit the statement that I'm talking about, but it does. So here's the example. So I want to prove if X is a real number, then X is less than or equal to the absolute value of X. Okay. Before I get to this proof, I want to write down the definition of the absolute value of X. So here, well, maybe I'll even say I'm starting the proof, and I will recall. I will start the proof by saying, let X be a real number. But just as a reminder to the readers and to ourselves, let's recall the absolute value of X. It's a piecewise defined function. It has one of two outputs. It's either, the absolute value of X is either X. When is it X? If X was
Non-negative.
okay, greater than or equal to 0. And the absolute value of X is minus X if X is less than 0. That's its definition. Let's just take for a second, if I were to, this is not part of proof, I'm going to erase this in just a second. If I ask you what the absolute value of minus 3 is, look, you don't have to follow the definition. We've worked with this and know. What's the absolute value of minus 3? 3. Okay. So the answer is 3. How does it follow this definition? The absolute value of minus 3 is either minus 3 or it's minus 3. Okay? It is minus 3 if minus 3 is greater than or equal to 0. But minus 3 is not greater than or equal to 0. Minus 3 is less than 0. So our answer is, to the absolute value of minus 3, is minus 3. Minus itself. Okay? Which is equal to 3. That's what we need to do. Okay, look, because of the definition of the absolute value of X, it kind of prompts us to break up the case of X being a real number into two situations, two cases. So if X is a real number, it's either X is really either bigger than or equal to 0, or it is less than 0. If you're a real number, you fall into one of those categories, and only one. Okay. So since X is a real number, we have two cases. I'm just going to write them right here. 1, X is greater than or equal to 0, or 2, X is less than 0. And so when you say that you've got a real number, you're either saying if X is bigger than or equal to 0, or X is less than 0, then X is less than or equal to the absolute value of X. So the first part of this statement can be replaced with if X is greater than or equal to 0, or X is less than 0, then this. And when you write it in that format, that statement, it fits this perfectly. But if P or Q, then an R. Okay? So that's how it matches. But we are breaking the statement up into a different translation so that we can use this type of proving technique on the statement. So what have I got to do? What I've got to do then is prove if x is greater than or equal to 0, then x is less than or equal to the absolute value of x. And I've got to prove that statement. And then I've got to turn around and prove if x is less than 0, then x is less than or equal to the absolute value of x. Okay, so case 1. If x is greater than or equal to 0, then, well, we want to involve the absolute value of x. Is that clock still accurate?
I've got a question.
No worries. I'm just making sure the clock's still accurate. Is that right?
Have I still got a few seconds, sir?
Yes, 2 minutes. Okay, 2 minutes. We'll finish this one. If x is greater than or equal to 0, what I'm going to be talking about is the absolute value of x. So what can I say about the absolute value of x? Well, it equals what? X. So x is equal to the absolute value of x. That means that x, I'll make this my subject of the next sentence, is less than or equal to the absolute value of x. Because they're equal. Equal means it's less than or equal to. So I got the conclusionary statement I wanted in this case. Okay. Case 2. If x is less than 0, then what can you tell me about the absolute value of x? It won't be equal to x, it'll be equal to minus x. Now, since x is less than 0, what can you tell me about minus x? Look, just concentrate on this part. If x is negative, what about the negative of x? It would be positive. That means it's greater than 0. Is that okay? So here, what I can have is x is less than 0, which is less than minus x. Okay, I'm just stringing these together. And that means x is x, but minus x is the same thing in this case as absolute value of x. So I've got that x is less than the absolute value of x, and therefore that x is less than or equal to the absolute value of x. Because in this case it's always less than. That means it's less than or equal to. Okay, I want to write down a conclusionary statement, and that'll be it. One of the things that's a kind of a practice that I want to adopt in my teaching style is I'd like to start on time, and I enjoy teaching, but I'd like to finish on time. Because you may enjoy this class, you may not enjoy this class, but you've got another class to go to maybe. And so you want to get to that class. I don't want to take up their time. Okay, so let me write down this conclusionary statement and we'll call it quits. Okay. So in all, this is what I write. So in all possible cases, if x is a real number, and our possible cases was x was greater than or equal to 0 or x was less than 0. X is less than or equal to the absolute value of x. I'm done with that. I put my little box, color it in, to indicate that I'm done. And I'm done with this lecture. Thank you very much. I'll post this on the Blackboard for this class site. I don't think it's been made available to you yet, but I'll make it available to you. So you can review your notes or you can see the lectures. And listen, when you find a mistake that I make, and I'm going to make some mistakes. I'm a person, okay? I'm going to predict that Florida State's going to beat Oregon. That's a mistake. I did predict that, okay? So I'm going to make some mistakes. When you see it, just say, hey, is that correct? You know, bring it to my attention. It'll help in the manufacturing of the lectures, okay? Thank you very much.